SwayamPrabha. Digital India. Educated India.
So, we will continue our discussion in this module, instability and tearing of sheets, and we have completed the theory part of this particular module, and we will now enter into the problem solving part. So, today we are going to solve 4 problems in this particular module. Question number 1, question number 2, question number 3 and question number 4. These are the 4 problems relevant to this particular chapter module. We are going to solve 4 problems. Okay. So, the first question is, the following figure, this particular one, shows a 100 mm length of a tensile test piece. Okay, total is 100 mm, 90 plus 10, in which 10 mm, that is this 10 mm, has a width of 12.4 mm. Okay, width is reduced, and the remaining is 12.5 mm. Okay, so we have a 100 mm gauge length, let us say 90 and 10. It is split into 2 parts, 90 mm, 10 mm. The difference is, in 90 mm you have the original width of 12.5 mm, but in 10 mm length, that particular part, you have 12.4 mm, 0.1 mm is reduced actually. So, all dimensions are in mm, you can say. But the entire sheet has got uniform thickness of 1.2 mm. So, T naught is nothing but 1.2 mm. So, this material obeys a stress strain law. It is given here, sigma is equal to 750 epsilon bar power 0.22 MPa. And so, let us assume that these 2 regions deform in uniaxial tension. Now, the question is, determine the maximum load, the final length of a 20 mm gauge length in the wider section. So, there will be one maximum load P max of the entire strip that we have to find out, and then in this wider length, that is your 12.5 mm, this particular part, you pick up a gauge length of 20 mm. Let us say at the center you have gauge length of 20 mm you are picking up. Okay. So, what is the final length of that particular gauge length? Okay. And the maximum strain in this section. So, in this 20 mm gauge length, what is the strain that is going to be encountered, okay, during this tensile test? That is a question here. Okay. So, this is like equivalent to what we have studied, like we are defining a thickness heterogeneity, right, TB by TA. So, where TB is your neck thickness or a groove thickness and TA is the outside region, right. Similarly, here also, instead of a thickness heterogeneity, you are having a reduction in width. A similar situation, we have solved one problem in the first lecture of this module, if you remember it. Okay. So, now when we are loading it in tensile test, we have to find these 3 values, P max, the strain in this particular section 20 mm gauge length, and what is the final length if that is the strain. So, directly we are going to write this particular one in a tensile strip. Okay. So, the load is given by P is equal to sigma 1 into A1, we know that, and this already we know, we already derived it. Sigma 1 is nothing but K epsilon power n, and A1 is nothing but A naught L naught by L1. So, A1 L1 is equal to A naught L naught. So, A1 is nothing but, so A naught L naught is equal to A1 L1. So, we want A1. So, it is nothing but A naught L naught by L1. Okay, that is what I have written here, and K epsilon 1 power n, then A naught would be your T naught W naught, and L naught by L1 is nothing but exponential minus epsilon. Okay. So, now what we are going to do is, when you are going to do tensile test of this, we know that this 12.4 mm width, this particular region is actually the weaker region, and hence in the narrow section, I am going to call this as narrow section, we can directly write the maximum load, okay, will be given by epsilon is equal to n. So I am going to modify this particular equation for maximum load in narrow cross section, in the narrow section. So P max, this P becomes P max is equal to K epsilon 1 power n will remain as it is here and here. T naught, W naught will remain same here and here. Exponential minus epsilon would become exponential minus n. Okay. So directly I am going to write this, and I am going to just substitute all the values. K is known, which is 750 megapascal. Okay. And so here also you are going to have n. So epsilon 1 will also become n. So n power n will be there. Okay. So this is n power n. Now epsilon 1 will become n. Okay. So either epsilon or epsilon 1, either way you can call. So 750 will be there, and 0.22 power 0.22 would come, and then T is 1.2 and W is 12.4 and exponential minus 0.22. So if you calculate it, it will come about 6.42 kilonewton. It will come about 6.418 kilonewton. So it is going to be 6.42 kilonewton. Okay. So this equation, we are simply modifying it for situation in maximum load epsilon is equal to n in narrow section. We are picking up narrow section, we are putting this condition. Okay, so that you can convert this epsilon 1 into n and this also as n, let us say, so that you can write directly as 750, okay, into 1.2 into 12.4 into your 0.22 power 0.2 exponential minus 0.22 would give you 6.42 kilonewton. Now let us come to wider section. Wider section, we will have the same equation, P is equal to K epsilon. Only thing is, instead of epsilon 1, I am putting epsilon 1a, because we do not know. That is what we need to find out. Okay. So P equal to K epsilon 1a power n. So T naught, W naught will remain here and here, exponential minus epsilon 1a. Okay. So but whether it is this region, wider region or a narrow region, okay, there will be only one P max. So what I can do is I can directly equate this to P max. So at maximum load, what I am going to do is I am going to directly equate this particular equation to your 6.42, which I got from the previous narrow region. From this narrow region, whatever I am getting here, this I am going to equate it to the situation in this particular wide section, because there is going to be only one P max for the entire strip. So I am going to say that 750 will be remaining as T naught 1.2 into 12.4, okay, epsilon 1a power 0.11 exponential minus epsilon 1a would be equal to 6.42, and what we can do is we can combine all the numerical values on one side, and then keeping this the terms having epsilon 1a power 0.22 exponential epsilon 1a, I am going to keep it as it is, and I am going to combine all the numerical values. It is going to be equal to 0.571. So what I am going to do is I am going to iteratively change this epsilon 1a value, okay, and see for which value of epsilon 1a I am going to get 0.571. Okay, so that I have just quickly took 4 different values and then plotted it here, epsilon 1a versus this entire thing, function of epsilon 1a. This I need to get this. So if I use 0.2, okay, here, if I use 0.2 or 0.2 here, so that I will get 0.5746, 0.18 I get 0.5728, 0.16 0.5694, and 0.17 if I put, you will see that I am getting 0.571. Okay. So from this table I can directly say we get epsilon 1a is equal to 0.17. So that is my maximum strain in this section. Okay. In the wider section, I am taking a maximum strain of 0.17. That is the next question. That is the answer for next question. So P max has been found out already, 6.42, and then in the wider section, I am going to have epsilon 1a as 0.17. Okay. And for this particular strain in that section, what will be the value of 20 mm length? Or 20 mm length, 20 mm gauge length in the wider section should become some value. What is that value? That you will get this particular strain. So it is very simple. So we know the original definition of epsilon 1a. So I can directly write the new length would be equal to the original length 20 exponential epsilon 1a. So this comes from the original definition of epsilon 1a. Epsilon 1a is nothing but ln of L by L naught, original definition, isn't it? So from that I can write this particular equation, and you will see that for this particular value of epsilon 1a I am going to get L as 23.17 mm. So that means when you are doing tensile test of this particular type of sample, and Pmax will happen at 6.42 kilonewton, and during that particular situation you will see that the strain attained in the wider region would be equal to epsilon 1a, that is along one direction, would be equal to 0.17, and this, when you have 0.17 strain, the gauge length 20 mm would become 23.17 mm. So at that particular stage you are going to have these three different values. Okay, so it is just a simple problem. Only thing is like we had two important points here. One is for narrow section, we are going to put this particular condition and get maximum load. That maximum load we are going to equate it to the same situation, similar situation in the wider region, that is in the A region, let us say. Okay, so and then finally we are going to get the strain and the corresponding gauge length, new gauge length, right? Okay, so let us go to the next one. Next one is also a similar geometry. So what is the question? The test piece geometry is used that it has got two parallel reduced lengths. One is 10 mm width, the other one is 9.8 mm width. Okay, so that's how the sample dimensions are. So width is 10 mm. Okay, in another section you are going to have 9.8 mm width. So in the wider section a gauge length of 50 mm is marked. Okay, so let us mark it. Okay, the strip is pulled to failure. Okay, so you are deforming the material and it goes to failure, and the gauge length measured to determine the true strain. Okay, so this particular gauge on 50 mm is used to measure the strain now. Okay, so now the question is, when you do that, suppose if you say that okay, you need to get that particular strain in the range of 0.05 to 0.2, what will be the change in strain hardening index or exponent, strain hardening exponent? That is a question. Okay, the strip is pulled to failure and the gauge length measured to determine the true strain epsilon A. Obtain a diagram relating true strain epsilon A in the range 0.05 to 0.2 to the strain hardening index. Okay, so that means how n value is going to change depending on the strain that you get in the gauge region. So that is the question, but the condition is the strip is not having uniform width, it is going to have a slight change in width. One is 10 mm width, the broader region, the narrow region has got 9.8 mm width. So since you are going to speak about n, then epsilon, okay, and then you are going to have some sort of area reduction between 10 mm width and 9.8 mm width. Okay, directly we can relate all these parameters by this particular equation which you already derived. N minus epsilon u is approximately equal to square root of minus n d a naught by a naught. With this we already worked out one problem in this module. So this equation can be used direct. So now basically you need to get relationship between n and epsilon u, and that epsilon u you vary between 0.05 to 0.02. We need to see how n is going to change. That's all. Okay, but for that you need to know this imperfection, severity of imperfection, so which is nothing but d a naught by a naught. So you can see that it is 10 mm width, 9.8 mm width. So the difference is, you can take thickness is not given, maybe you can take thickness of 1 mm, let us say. So if that is the case, then it will dA naught would be minus 0.2 divided by 10, which is nothing but minus 0.02. And as per this equation, n minus epsilon u is equal to square root of minus n dA naught by a naught, that will be equal to 0.02. So minus minus will become plus 0.02 into n. So n minus epsilon u whole square would be equal to 0.02 n. Okay, so now you can expand this, n square plus epsilon u square minus 2n, epsilon u would be equal to 0.02 n. So and you will see that this will be a in the form of a quadratic equation. So you can see that n square minus 2n epsilon u plus epsilon u square is equal to 0.02 n. This is nothing but n square minus 2 epsilon u plus 0.02 n plus epsilon u square is equal to 0. So ax square plus bx plus c is equal to 0. It is of that form. So you can find root of this equation as so this way. So n is equal to, okay, you can say minus b. So 2 into epsilon u plus 0.02 plus or minus square root of b square 2 epsilon u plus 0.02 to the whole square minus 4 into 1 into epsilon u square by divided by 2. Okay. So, you can simplify this to get in such a simpler format where n is going to vary with respect to epsilon u in this way. Okay. And it is said that if you change epsilon a or in this case epsilon u, okay, because you are saying that it is pulled into fracture, no. So, there is nothing wrong in keeping this epsilon a as epsilon u in this equation, both are going to be same. So, now if you change epsilon a, let us say 4 different values you take between 0.05 and 0.05, let us say 0.1, 0.15 and 0.2. If you substitute here, what is the value of n? So, you may get 2, you may get a range because there is a plus minus. Okay. So, you may get a range which is what I plotted here. So, if you change epsilon here 0.05, you may get one limit for 0.0, next limit for 0.1, then 0.05 you get another limit, and 0.2 you get another limit. So, obtain a diagram. So, this is the diagram we are going to get, which basically tells you how n changes with respect to this epsilon a. Okay. So, depending on epsilon a, n is not going to be a constant, n is going to vary in this fashion. Okay. So, this is your next problem. So, your third problem is also relevant to your imperfection related. Okay. So, this problem is also very important for us to understand what we studied before. So, this diagram you can refer, this diagram is known to us. Okay. This was used before for some theoretical explanation. So, you have a sheet which is pulled in both the directions, let us say sigma 1 and 2 principal stresses in one direction, two direction, and let us consider A region and B region. A region is actually it's a uniform region, B region is like a groove you can say, or a neck region. So, where thickness is going to be TB and outside is going to be T. So, this is where we defined F is equal to TB by TA, if you remember this, right. So, this is the situation we have. So, what is it said in the question? An element of material has an imperfection characterized by F naught is equal to 0.995. It's same as that of F, but we know that the F is not going to remain same. So, we say F naught as shown in this figure here, this particular figure. Okay. So, that particular material has got this imperfection defined by 0.995. So, small imperfection value. Okay. So, it is deformed in equibiaxial tension, that is given here. Okay. So, sigma 1a equal to sigma 2a. So, sigma 1a will be equal to sigma 2a means, that means with respect to a location, with respect to a region. Okay. With respect to a region, your alpha is no. For biaxial tension, alpha is nothing but 1 you can keep. So, and the entire material is going to follow this particular stress strain law, sigma bar is equal to 600 into 0.004 plus epsilon bar power 0.2, and you know the fact that this is nothing but your pre-strain value, such a small value 0.004 MPa. Okay. So, pre-strain value. So, now what is the question? Determine the principal stresses. Principal stresses means you have sigma 1 and sigma 2 and the stress ratio, that is nothing but alpha in the groove region when the uniform region starts to deform. When the uniform region just starts to deform. So, this A region is just going to deform, start to deform. At that particular situation, you need to get principal stresses and stress ratio in the groove, that is B. So, I am going to say epsilon B, 1B and 2B. These three values you have to evaluate. So, which means that one should understand the fact that the sigma 1a, 2a, alpha a are not going to be same as that of this. That is why this question is actually asked. Right. So, first of all we need to evaluate these three values in the B region, that is in the groove region. This B is nothing but your groove region because your thickness is less. A is a uniform region. So, now when the uniform region starts to deform, so that is a key point. Okay. We can say that for both the elements, if this is the situation, the material has zero plastic strain. Okay. It's just going to deform. Okay. So, if the plastic strain value is given, you can directly use it. If it is not given, then we can simply say material has zero plastic strain, because we do not have any other reference of what is the strain when the uniform region starts to deform. Okay. It may have small value, but then we do not have it in the question. So, we can simply say that this epsilon bar, which is nothing but plastic strain, let us say, this is going to be 0. So, that your effective stress sigma bar becomes 600 into 0.004 power 0.2, which is about 198.9 megapascal. Okay. So, this sigma bar has been obtained now. Okay. So, when the uniform region starts to deform, suppose if plastic strain epsilon bar is some values given, then we have to use that value to get a sigma bar. So, which is not going to be this, it could be slightly some other value. Okay. So, now given the situation, we are saying that this fellow is going to be equal to 0. Okay. So, now let us come to A region, which is a easy region for us to evaluate certain things. So, in the A region now, because I know sigma bar, I have to relate this sigma bar to one of the principal stresses. So, directly we are going to use some yield function, and well known yield function right now for us is nothing but your von Mises yield function. So, as per von Mises yield function, we can directly write sigma bar divided by square root of 1 minus alpha plus alpha square equal to sigma 1. We say since it is a region, I am writing sigma 1A. So, suppose if you put alpha is equal to 1, because we say that it is the A region, or in the uniform region we say that it is balanced or equibiaxial tension. So, alpha is equal to, let us say, 1. Okay. So, this also is 1. So, 1 minus 1 plus 1 square root goes off. So, sigma bar will be equal to sigma 1A. Sigma bar is equal to nothing but sigma 1A. So, what does it mean? That means we can directly write sigma 1A is nothing but 198.9 megapascal. 198.9 megapascal. So, we need to find sigma 1b and sigma 2b. So, now what we have done is we have found out sigma 1a. Sigma 1a has been found out. Okay. Then, if you know sigma 1a, sigma 2a can be found out, but that may not be useful for us because we know alpha. Okay. So, it may not be useful for us, it will be same. So, but it will not be useful for us. So, directly we are going to B region. So, in B region, okay, if you want to go to B region, then we have to use some already known value, that is sigma 1a. Okay. So, if you want to find sigma 1b, my aim is to find sigma 1b. So, sigma 1b has to be found out with a known value, let us say sigma 1a. Then the best relationship that I can find out is nothing but my f value, isn't it? So, we have already derived that f is equal to Tb by Ta. From here, we have derived the stress ratio also, okay, in connection with f, okay, and that is what is given here. So, sigma 1b if you want, that will be obtained by sigma 1a divided by f naught. This we already derived. Sigma 1b if you want, you can have sigma 1a divided by f naught. Sigma 1a is 198.9 and f naught is nothing but its initial f naught is 0.995, and that will give you sigma 1b is about 199.9 megapascal, right. So, it is okay, like for example, sigma 1b is 199.9 would be larger than sigma 1a, that is what is given to us. So, now what I am going to do is, I am going to now sigma 1b is found out. So, this value is now ready. Okay. So, now this value is ready. So, now I need to find out, let us say sigma 2b or alpha b. Okay. If I know alpha b, I can find sigma 2b, or if I know sigma 2b, I can find alpha b. But now what I am going to do is to find out alpha now. So, now the same thing. So, if I know sigma 1b, major principal stress is known. If I want to know alpha, the simple relationship what I have is von Mises yield function. So, I can directly write for region B also sigma bar divided by square root of 1 minus alpha plus alpha square is equal to sigma 1b, which is nothing but the sigma bar is nothing but already known 198.9 divided by square root of 1 minus alpha plus alpha square, which would be equal to sigma 1b, which is 199.9. If you simplify this, you will get alpha as 0.99, which is not actually 1. You will see that the with respect to A region, sigma 1a would be equal to sigma 2a, which is given, but actually if you calculate alpha in the groove region, it is slightly less than 1. It is not equibiaxial tension, it is biaxial tension, but alpha is not equal to 1, there is a change. So, one has to be a little bit careful and understand this particular thing, and that is all. So, if alpha is known to me, so now I can find sigma 2b, because sigma 2b is nothing but alpha into sigma 1b, which is 0.99 into 199.9, which will give me 197.9 megapascal. Okay. So, I am going to use two important relationship. One is my von Mises yield function, sigma bar divided by square root of 1 minus alpha plus alpha square equal to sigma 1, and then this particular relation sigma 1b equal to sigma 1a by f naught. Okay. These two relationship, this one and this one. These two expressions are actually used to evaluate the entire problem. So, region A, region B, okay, are divided, and we can apply these equations appropriately to get a required answer. But again I am telling, if the uniform region starts to deform, if some strain, effective strain is given, we have to use that instead of zero plastic strain. So, now here we do not have choice to assume it to be 0 even at the start of the deformation. Okay, so, this is the third problem. So, now let us go to the fourth one, which is a general one. Okay. So, now assuming that tensile necking begins at maximum load. Okay. So, that we already put this condition, isn't it? So, we already said that your df is equal to df or dp is equal to 0, right? Begins at maximum load. Find the actual true strain epsilon at necking for the following material loss after deriving a general equation. Okay. So, basically you need to get the actual true strain at necking. So, basically you can say epsilon u you want to get, okay, at necking. But only difference is there are 3 different stress strain laws that is given, and some specific values are given to get some actual values for this epsilon u. Okay, one is sigma is equal to k into epsilon naught plus epsilon power n. This equation we already know, where f naught is your pre-strain. That value is given 0.05 and n is also given 0.25 and k is given as 500 megapascal. There is next equation, sigma is equal to sigma naught plus k epsilon. This is a very linear equation between true stress and true strain, and sigma naught is nothing but 250 MPa and k is about 350 MPa they have. And another one is a trigonometrical function. Okay, sigma bar is equal to k sine b into epsilon, and k is given as 500 MPa, and your b is let us say 2 pi. So, since it is tensile necking begins as maximum load, you want to get actual true strain, we are going to put the same condition which we derived before, that is d sigma by d epsilon would be equal to sigma, or 1 by sigma d sigma by d epsilon is equal to 1, we said, isn't it? The same equation can be used here. So, sigmas are given, so you have to differentiate and equate it to the same equation, get a general form of the equation, apply these values, you will get epsilon u. That would be the approach. So, sigma is equal to k into epsilon plus epsilon naught power n. So, d sigma by d epsilon would be n k epsilon naught plus epsilon power n minus 1, which is nothing but sigma. D sigma by d epsilon is equal to sigma. So, this sigma is nothing but k epsilon plus epsilon naught power n. So, you can equate like this. From this you will get n is equal to epsilon plus epsilon u, and epsilon u would be equal to n minus epsilon naught. N is already given as 0.25. Epsilon naught is 0.05, so epsilon u would be 0.2. Okay. So, this is a straight line fit, sigma is equal to sigma naught plus k epsilon. So, which is nothing but y is equal to mx plus c. Slope of this curve would be nothing but slope, and slope will be nothing but m only. So, you will get t, k. D sigma by d epsilon is nothing but k. This d sigma by d epsilon is nothing but sigma, which is nothing but sigma naught plus k epsilon is the original equation. So, from this you can get epsilon u as 350 minus 250 by 350, which is 0.29. If sigma is equal to k sine b epsilon, then d sigma by d epsilon is nothing but k cos b epsilon would be b, which is nothing but k sine b epsilon, which is nothing but sigma. So, from this you can get epsilon as 1 by b tan inverse of b. So, epsilon u is nothing but you can substitute 2 pi here and you may get some value. Please check it. This would be your epsilon u. So, 3 values of epsilon u all are different. These are going to be different. These are not going to be same. Okay. So, the condition remains same, that is tensile instability condition at maximum load is being applied, but if you change the material loss which the material is going to follow, okay, then accordingly your epsilon u prediction is also going to change. It is not a small change, it is going to be a good change. This could be 0.2, this is 0.29, this could be maybe 0.22, maybe or 0.23 will come. So, all these values is going to tell you finally that depending on the material law, the instability prediction is going to be different. Okay. So, we have seen 4 problems in this. So, 4 problems. Okay. So, here we have used the maximum load condition at the narrow section and got P max, and use that P max to apply the same thing to the wider cross section, okay, wider section, and in this, okay, from this you can get your strain at that particular maximum load. If that is the case, what is the length in a small part of that wider region is what we found out. Next one is Similar situation, you have a narrow region and wider region. If it is pulled up to failure, now they are asking us how to find out the variation in n with respect to the strain values within a small range of strain. So, in that way we looked into the problem. The tone of the problem is basically to relate n, epsilon u and the imperfection. So, we started in this way. Third one is straight away that our balanced biaxial tension situation, and then the situation in the uniform region, that is in the A region, is given to us. Now, we wanted to find principal stresses and alpha in the B region. So, here also we have used two important expressions. One is the von Mises yield function expression and the heterogeneity factor F, but not related to thickness. We have already converted that into stress ratio. That is what we have used here in the second equation, and then we have found out all the values. The fourth one is a very general one. Okay, suppose if the material fails at the instability, okay, the maximum load, then you want to find uniform true strain. Okay, so then in that case, how material law is going to change the value. So, that is what is given here. So, with this we stop. The next module we are going to start a new section.